Hey guys, I'm Jeffrey, and today we're going to be looking at a very interesting math problem. So the other day, I was looking through my contacts, right? Looking at the phone numbers. And I was wondering how many phone numbers exist where the digits are non-increasing. And that's the inspiration for this problem. How many 5-digit positive integers exist where the digits are non-increasing from left to right? So 87,743 satisfies this because it's all non-increasing. They can either be the same digit or decreasing. And this one, 10,000, also works. Now the problem is 78,987 does not work, and 33,429 does not work. So how do we solve this problem? What I always like to do for a problem is write down some intuition. So we know that between 10,000 and 99,999, there are 90,000 5-digit positive integers. And let's simulate this. Sometimes if you don't have an idea, it's best to write something down. So let's say our first digit was 7. We chose 7. Now the next digit has option 0 to 7. So let's pick a 5. Now let's look at our next digit. Next digit can only be 0 to 5. Looks like we shrank our possibilities. We had 8 possibilities before, now it turned to 6. And now it goes to what, a 3? Let's say we pick a 3. Then our next digit can only be 0 to 3. That's very limited. So my gut feeling right now is that there are very few increasing numbers. It's going to be a pretty small fraction of 90,000 that are increasing, or non-increasing. But this is just our intuition. How do we solve this problem realistically? Let's go back to our case. Let's go back to our simulation. So we have a 5-digit number right here. How many possibilities can we choose for the first number? Well, there are 9 possibilities. What if we just go this method? 10 possibilities, 0 to 9. Or actually, no, only 9 possibilities, because you can only have the digits 1 to 9, 9 possibilities. Now the second digit, it depends on what you do for your first digit. So how many cases is that? Well, I actually don't know. It's got to be 0 to whatever something, some x right here, right? And actually don't know. Is this like an x? And then how many possibilities here? It has to be 0 to, say, y. Or x plus 1 numbers. 0 to y, if we picked a y, there's going to be y plus 1 possibilities here. Now this is kind of difficult. Why do we have so many variables? We're going to end up with so many variables. And I guess like no way to really solve this, because then we'll have so many cases. So I'm feeling like there is an easier method. This method probably does not work. Let me let you in on a secret here. Combinatorics problems are notoriously difficult because oftentimes there's a really clever construction that you need to think about to solve the problem. Otherwise, you're just stuck. So let's try thinking about this problem in a different way. Imagine, we take the example 87,743. Let's look at how much it decreases by. Decreases by 1, 0, 3, and 1. So how do we conceptually grasp this idea of decreasing? The problem is we can't really grasp this idea and put it into mathematical notation. Well, let's try representing these decreasing units with maybe just a dot. So 8, we decrease with a dot to 7. 7, we have no dot. Then we have 3 more dots to go down to 4. And then we add another dot and we go down to 3. So now we have this. Now remember, we could have also started with 9, right? This is like the invisible. You have like the invisible unit right here, the invisible decrease here. And we have the invisible, basically 0. We end with 0. These are like invisible dots, right? Now, that's the problem. If we just counted using our first method, the problem is we could start with different, starting and ending points, and that would be very hard. A lot of cases to calculate. So now let's look at this. If we can do this, right? Let's say we can represent any number in this way, right? We can do a 9. So we have a 9, and then we can have 2 dots. We get a 7. We have 2 more dots. We get a 3. We get 1 more dot. Maybe we have like a 2, no dots here. 2, 2, and then 2 more dots, 0, and 0. Oh shoot, I messed up here. Oops. 7, 5, 4, 4, 2, and then 2 more dots, and then we have a 0. We can represent any number using 9 dots, and we just need to decide where to stop to get our next digit. So here we had 2 dots first, and then we stopped to get our next digit. We had 2 dots, stopped, stop, and then we stop. Now this is looking awfully similar to something else. What if we represent these numbers with bars? Doesn't this look like stars and bars? Stars and bars. That's very interesting. We turned this problem into a stars and bars? I never expected that. This is really cool. Wow. Well, it seems like we can represent any number using stars and bars, right? If we just permute this stars and bars thing, we can get all the numbers that are non-increasing. Like, say we had a bar, we can interpret any permutation of stars and bars like that. Or let's pick a very interesting case. And we have 9 dots. We can interpret this as, because we start at 9 when we end at a 0, we interpret this as 9, 9, 9, 9, 9. That's non-increasing. That works. That does indeed work. Looks like every permutation of this stars and bars corresponds to one number. So all we need to do is count the number of ways the stars and bars this works, or number of stars and bars permutations. So how many are there? there are 9 dots and there are 5 bars. So out of the 14 objects, we choose 5 positions where the bars land in. That is equal to 14 times 13 times 12 times 11 times 10 over 120, 5 factorial. And we can just cancel out the 12 and cancel out the 10. 14 times 13 times 11. Maybe you have to do some multiplication, but let me let you in on another secret. 7 times 13 times 11, or 7 times 11 times the 13, that is always equal to 1001. Now remember this fact. This is a very useful fact because 1001 shows up in many problems, many competition problems. It shows up all the time. So this fact is very useful for this problem, especially because we have 14 times 13 times 11. 14 is a 2 times 7. So we have a 2 times 7 times a 13 times 11 here. So we know that this is going to be 2 times 1001, which is 2002. So that's the number of non-increasing numbers. It's 2002. That's the answer. And from our intuition, we had 90,000 numbers originally. And 2002 is indeed a very small fraction of 90,000. Wow, I never could have expected that this problem just boils down to a stars and bars. Like, I always admire combinatorics problems because they have amazing constructions. Like, how would have you expected that this problem you can just turn, decreasing units into dots and then the digits into bars, and then you get your answer. Like, that's so beautiful, so wonderful. Anyways, that's it for today. I hope you guys learned something and found it a very interesting problem. I'll see you next time. Thank you.